Next up, we have two speakers who are trying to build a new generation of hardware for artificial intelligence. They're designing chips for AI, optimized for AI that will help these powerful algorithms realize their full potential. Their startup, called Tenstorrent, was founded just 6 years ago and aims to make general-purpose AI processors that programmers can use to do a wide variety of tasks more easily and efficiently. Ljubisa Bajic is CEO and founded Tenstorrent after holding senior roles in chip design at NVIDIA and AMD. And Jim Keller is Chief Technology Officer and has had a celebrated career in hardware with time at Intel, Tesla, AMD, and Apple. We'll be talking here for about 30 minutes, and we will take some of your questions. So please start thinking about what you would like to ask Jim or Ljubisa. Ljubisa and Jim, welcome to Future Compute. Hello, thanks for being here. Please take a seat, and we will get started. Welcome to the stage.
Right.
All right, here we go. Ljubisa, I want to start with you because you are the CEO and began this new company. Tell us about Tenstorrent and summarize for us what you're trying to achieve and what your vision is with this new startup.
So we were watching Daniela's presentation from the room over there, and she talked a lot about all sorts of robots. She didn't talk about the upcoming robotic invasion. But if we're going to enable that, there's this implied assumption that there's a lot of computing machinery behind it, right? Like both a lot of the smarts that the robots were demonstrating usually are implemented using some mixture of classical programming and machine learning neural networks. The neural networks need training. They've been growing in size for the robots to get better at stuff and for a bunch of other things like chatbots that you mentioned earlier. So the size of the computing machinery and the computing problems literally exploding exponentially. On the other end, putting something like this into a little battery-sized device that can be swallowed and go into a kid's stomach requires super low power, lower power than things that we're currently doing. And thus, you've got this kind of paradoxical situation of desiring massive, bigger than ever compute machinery on one end, and then tiny, super low power, lower power than ever, still computing machinery on the other end. So 5-6 years ago at this point, we thought that this is putting strain on current approaches to computing that they're unlikely to be able to resolve without a major shift to how this stuff is done. That we need to build computers that are special built, special optimized for this. That basically the way we still today do AI is actually going to need to get a lot smarter. Mm-hmm. So right now, if you analyze and dissect a neural net, it's basically a sequence of matrix multiplications. Jim's got this funny statement that he often repeats where he shows a bunch of equations. On the one end, they look like very serious math, and on the other end, he goes, well, but it's all like A times B plus C, right? Like at the end, and it kind of is, interestingly enough. So we think that needs to change. The A times B plus C needs to become a thing that's more intelligent, where portions of the A and B and like the C are used depending on what the input into the robot, for example, is, what the robot is seeing. Is it in a stomach or going down the esophagus? Well, whatever you kind of choose to define its pertinent state as. So current computers are bad at that. We wanted to build computers that are really good at that, and we wanted to make them such that we can easily scale them from the super high-end, very large installations to the stomach-bound tiny little robot.
Mm-hmm. Thank you for that summary. And Jim, I want to ask you, you're a really well-known person in the field of hardware engineering, very highly respected. You've had an incredible career. Some of the phrases that came up as I was reading about your career are things like hardware ninja, legendary chip architect, microprocessor mastermind, just to name a few. So you have a lot of options, I imagine.
You missed guru.
Guru, I missed Guru. Yeah, I'm sure that's in here as well somewhere. So you have a lot of options, I imagine, just for how you want to spend your time, what you want to work on. Before you joined Tenstorrent, you were actually, I believe, one of its first investors as well. So you've really gone all in on Ljubisa's concept here. So what about that vision resonated with you? Why Tenstorrent right now for you?
Well, first I want to say I encourage people to say things like that in articles. Just in case you're wondering, I'm not
You
shy about
suggest
it.
them?
'Cause I forwarded it to my two daughters who were teenagers, and they're like, Dad. I said, really? I was in the Times of India. So I think that's really funny. If you control your own kids, you're in good shape. So AI is so weird. Like Ljubisa just said, it's like a milliwatt to 10 megawatts. Like that's a really wide range in computing for fairly similar models. And then like the world today is, cloud computing, mobile computing, and then there's a little bit of AI, and they call it AI acceleration, right? And the world's going to flip over. It's going to be 80-90% AI computing, not too distant future. So I really want to work on that, and I like what Ljubisa is doing. I talked to lots of AI startups, and he was one of the few guys that was actually a chip person, a mathematician, and could write software, which is, by the way, a killer combination. Students, it's a pretty good thing to be able to do, and I like what they're doing. And then starting like yet another AI startup, and there's already 50 or 100 of them flailing around. Didn't seem like the right answer, so. Yeah, we joined forces, and then we're building AI computers and then regular computers, general purpose RISC-V CPUs, and then we think the interaction is going to be interesting. And then the recent papers about pathways and the singularity from Microsoft and Google kind of validate this idea that the AI and the general purpose computing are going to work together. And then solving this problem is hilarious. And as best I can tell, AI computers are somewhere between 10,000 and 1,000,000 times too slow for what we'd like to do. And that's, it's not completely unprecedented. When Toy Story came out, people wanted that real time. It was 25 years before, Unreal Engine could do it. But that's where we're at. It's a wild place to be. Like, supposed to be, we're off by a factor of 2. Now we're off by a factor of 1,000,000. Like 1,000,000's a big number.
Yeah. Well, just to follow up on that, I mean, you've both talked about how AI is going to overtake computing. Can you say more, Jim, about kind of what do we mean when we say that, and what do you think it means for people watching, either in the room or online, who are on technical staff themselves or managing a technical team? What should they be doing now to prepare themselves for that shift?
You ask me?
Yes.
Okay. Let's see. So, I tell people I've been working on computers for 40 years, and basically for 40 years. Computers ran assembly code and C code, right? Like I know there's Java, JavaScript, HTML, there's all kinds of stuff, right? But if you compile, somewhere in there you compile it down to either C code or assembly language programs. So for 40 years we made that go faster. And it solved a whole bunch of problems. Like if this is true, then do this, else do that, right? And then it turns out it couldn't solve a whole bunch of other problems. Speech, image recognition, like it didn't solve any of those problems. Like I know people who spent 30 years doing, what they call classic vision, and they couldn't find a cat, right? Literally. So so there's problems that declarative serial programs can solve, and then there's all the rest of the problems. Like actually, we don't know yet what AI can't solve, but the number of things it can solve is really big and interesting. And so working on that is kind of amazing. So, and it's interesting what a big breakpoint that is.
Yeah. Ljubisa, over to you for this one. A lot of companies have been trying to build these really specialized chips and have been leaning really hard into that for AI. You guys took a really different direction with the ones that you're trying to build. Why did you decide a more general approach was the right one for you at this time?
Well, I think the most obvious answer is that the field's still evolving, and there's been fairly large changes in what the most popular neural net architectures that people use, both for vision and control system type applications like in robots, as well as understanding language, understanding speech. So far, anybody that's hardwired aspects of existing architectures in their solution hasn't really lasted for more than a year or two, like before becoming somewhat irrelevant. And in general, if you zoom out to Jim's 40-year time horizon, you've had this kind of question pop up a lot of times outside of the space of neural nets, where people thought that they could hardwire some interesting functionality and really forego software and make it more more specialized for the efficiencies that brings. And it was wrong every time. It's so like sticking with the graphics example, mid-90s, people came out with graphics accelerators that were pretty hardwired, although there was some programmability to them. Over the next decade, they became fully programmable. And that's a story that repeats a bunch of times. Ultimately, there's always going to be some customization, some new idea to apply. So that's really the answer, I think.
Yeah, that makes sense. And just to stick with you for a moment, I mean, you're not the only one in this space. You've certainly got some competitors, even some of your former employers, AMD and NVIDIA. So what else do you feel like is different about your approach, and what will set your products apart?
So I'll kind of double down on some of the points I did in the intro. So most of the machinery out there today is built for running a sequence of very large matrix math. Matrix multiplies other types of matrix math less. We've hit a point where some of the bigger models out there are so big that the next step is just not on the horizon. Like, even though some of the companies you mentioned basically have been doing very well, keeping up with the demand and producing chips that are doing better and better generation over generation, we're still at a wall. So a popular model out there is called GPT-3. OpenAI made a lot of noise. Lots of people are familiar with its functionality. GPT-4 being as much bigger over GPT-3 as it was over GPT-2 is currently not doable. So we try to solve that problem, and the way we chose to solve it is by making the computing machinery more intelligent as opposed to just bigger, so that you can go in there and be very specific about what parts of the computation are needed for a given task, for a given input into the model. I think we're really quite unique in that. Like, so far, everybody else is focusing on bigger, more. Another interesting thing is that a side effect of the desire to go milliwatts to megawatts was that we made a software stack that can compile machine learning models into all of these without having to tweak them, change them, deploy a team to do conversion, which is the norm today. So those are probably the top two things that are different for us. And then when you double click what each one of those means, there's massive implications on compute hardware, networking hardware, the way the whole thing looks, top to bottom.
Yeah, and since you brought up GPT-3, Jim, I want to come over to you for this one. There's a lot of debate right now about these massive AI language models. A lot of people see them as the future of the field, calling them foundation models, but they're using huge amounts of data. You have a different perspective on that, I think. So what is your read on that, and how important this will be to the future of AI?
Well, so we're in this interesting spot because the internet grew, and then everybody got lots of data, and then we said we have this big data thing, and then AI came out, and we trained it with big data. So how many people here use big data to learn anything? Like, that's not how humans work at all. We mostly learn by thinking, and then by having ideas and then elaborating those ideas. So big data is unreasonably effective, which is really cool. At the same time, it doesn't look like intelligence yet, but then it does stuff that's kind of spooky, right? Mm-hmm. And then the hardware to train the language model, is unbelievably big and expensive, right? And I joke, the autonomous driving guys are all collecting millions of hours of video to train a computer to drive. Mm-hmm. I taught my 2 daughters to drive in about an hour. It wasn't that hard. I didn't give them any video at all, like that I remember. And I don't remember them looking out the window much when they were kids, because everybody's doing something, right? So there's a really interesting split on how this stuff is working. So I think we'll start to see AI models that learn by creating models and simulating things. On the flip side, AI models are really good at forming massive associations between things. And that part of machine learning is actually smarter than what we think of as human level intelligence. Like, they can relate things way past what humans can do. Mm-hmm. Jeff Dean had this picture of, here's AGI and then ML is a subset of it, and that's actually wrong. Here's AGI, and then ML is this other thing, which at some level is already bigger. but the way it's built is unbelievably expensive and complicated. And while big data is really effective, it doesn't seem intuitively like that's the thing that's actually going to work long run. So yeah, we're very interested in how this is playing out.
Yeah, I mean, I'm glad you brought up this concept of intelligence. Just to go even broader on you for a moment, I mean, we sometimes hear about, the goal being to mimic human intelligence or approximate it, but, I don't know that is necessarily what you're working towards. So what is kind of your current thinking on intelligence and how you're thinking about developing machines and AI that
well, let's split it up. So we're a silicon company building chips, right? And then we're going to build a software stack so that AI programmers can write code, compile it, and run it and get good results, right? Without having to have like an army of people hand coding matrix multiplies to go faster, some pile of libraries. So that's our mission. The amazing thing about the AI world today is there's thousands of researchers and they publish, right, all the time. And then if some new model is really good, everybody goes, holy shit, that's a way better model than this model. And they copy it. And then everybody does their tweaks. And so there's this interesting, like we're in the early days of exploring this. Norm Jopi is a really smart guy. He's one of the TPU architects. I worked with him years and years ago on a processor. And we were building a bipolar MIPS processor at a gigahertz when a gigahertz was a big deal. And bipolar transistors were getting faster like this. And CMOS transistors were getting faster like this. And he calculated the day that CMOS would be faster than bipolar, and we canceled the project. It was like, that's kind of wild. So right now, human intelligence is flat. We're not getting any smarter. Is anybody getting smarter? I don't think anybody's getting any smarter. But artificial intelligence is getting smarter really fast, right? And then there's this difference between what we think of as intelligence, which is our opinionated, judgmental, planning. It's an interesting thing what we think intelligence is. And then there's what machine learning is, which is this massive data association capability. And both of those things are growing pretty fast. And it's not obvious at all that we'll, quote, get to human intelligence, because the day we get to it, the day after we'll be past it. And the curves are very different. But then how people use intelligence, it's kind of unknown. So
yeah, story's still being written.
Yeah.
I do want to open it up to the room. I suspect there might be some questions for Jim and Ljubisa among those of you here. If you do have a question, raise your hand and we will bring you a microphone and give you a chance to ask it. First question. Yes.
My name is Vivek Pandit. I'm at Boston University currently.
Would you mind standing up, please?
Oh, sorry.
Thank you.
I beg your pardon. So some of us were having a conversation after day one last night, and the observation was made, and I'm just picking up on your observation, that if human intelligence is doing that, it's flat mostly, and machine intelligence is arcing upwards, whether it's linear or logarithmic, whatever, who knows. What is the future for human, again, you're speaking, obviously, you're designing the chip layer of the entire stack, but as you look at the ecosystem, any thoughts about what the future looks like, and in terms of the role of the human versus this other constructed intelligence we're working so hard on? It sort of overlaps with what Daniela also talked about a little earlier.
Well, it's hard to talk about what's going to happen in the meta reality of superintelligence. Like all kinds of things are going to happen. But in terms, like I'm an engineer, I like to design stuff, right? We're starting to apply AI to writing code, to doing chip placement, to do synthesis. There's a whole bunch of things. Like they're going to apply this to material science, to data analytics. Like there's so many things we're having the ability to do, like machine learning driven computation is going to be really useful. And like the bright side of it is there's so much stuff to do. Like there's so much stuff, like I'm fascinated what people can do in material science. Like we've scratched like literally just the surface of what's possible in manufacturing, material science, all kinds of things. So the applications of machine learning are going to be wild. I think machine learning is going to replace basically graphics as we think of rendering today. Like, the ability to say, hey, create this object and do this, the famous holodeck experience. That's going to happen. Like, it's happening really fast. And then people who grow up with it are going to interact with it as that is a natural part of their world. Like I think it'll be mostly good. But what the world's like with, actual superintelligence that's opinionated like us, we'll see. I don't know.
Other questions here in the room? Yes, back there.
Hi, this is Girija from JP Morgan Chase. So we are moving towards the platform agnostic world, right? And then if you're building specific computers to solve the AI problem, how does that fit into the paradigm of platform agnostic software development?
Ljubisa, do you want to take that one?
Sure. So I acknowledge and agree with the desire to be platform agnostic, and I think it's going to happen. I just don't think it's going to happen as soon as is commonly expected right now. And the reason for that is that if you sort of double click on these ideas of not just running a bunch of generic math and trying to adapt the way you execute machine learning models to what they're being faced, like what they're being stimulated with it at a given moment, that opens up a lot of angles for compatibility type problems between different solutions. So anybody can run big matrices relatively fast. It's easy to pack that up into a solution that's totally platform agnostic and hidden. The moment you break that paradigm and try to do something more intelligent, there's an explosion of possibilities, which we've already seen happening. So if you observe NVIDIA's recent parts, like beginning with the one they put out 2 years ago and continuing with the recent one, they're building in features which make models tied to their hardware, right? Like at a very low level, especially for inference. That's a necessary thing. You're going to see it from us. You're going to see it from anybody that really becomes a serious player in this space. So eventually, I think people are going to get to the point where they look at all these features that vary across vendors and standardize them in some way and make them such that you can really build a platform agnostic solution on top of it. But I really think that that's a few years away, and before that happens, well, it's going to get worse before it gets better, right? So like what you'll see is that my prediction anyway is that places like NVIDIA have their own pipeline from milliwatts to megawatts, same kind of story. If you train a model on their platform, it's going to work a lot better on their edge device. And anybody that's serious in this space is going to be doing the same thing. Somebody's ideas are going to win out. Eventually, they'll get standardized, and we'll get to this platform agnostic thing. But for cutting edge stuff, especially big models, GPT-3, or tiny things that go into robots that are challenged at the level of scale and power, platform agnostic isn't around the corner, I don't think.
Yeah, and I just want to interject. So people like platform agnostic, but like if you look at the history, there was all these mini computers, that's where I started, which proprietary Unix implementations, and then there was standards for it, POSIX compliance and stuff. And so while they were screwing around, making Unix standard, Microsoft created a super cheap platform, which was a Microsoft product, but everybody could go on top of it. Intel, ironically, was the open source platform. There were 7 licensees of the Intel architecture, which is why they built other people, but that slowly turned into monopoly. And then the internet came out, which was a wide open platform. And then that was followed by the app stores, which was completely a closed garden. So you see the pendulum swing back and forth. And then, people are talking about, like, what's the metaverse going to be like? And nobody really knows. And then the AI researchers is one of the most open free-for-alls I've ever seen. The leading researchers publish, and you can mostly, if you're an expert, decode their paper into something you can replicate. And then you could go try it out. But then the big AI machines are so expensive, very few people have access to them. And one thing we'd really like to do is seriously lower the cost of big AI training and inference so many more people could have it. And we also believe in open source software, which we're going to open source a whole bunch of the software stack. But this pendulum swings back and forth because at some point when there's a really great product, people are willing to use that despite, let's say, the platform limitations. And we've seen this cycle happen in very curious ways over the years. But it's a really interesting question.
Yeah, just to end on one question, I'll point this one to you, Ljubisa. I mean, you've both worked for major chip manufacturers and ran large teams, had significant resources. Curious as to what led you to start your own company and do this on your own versus working within one of those existing companies.
Well, part of it is unexciting. I just wanted to start my own company for a chunk of time.
Fair.
But the other part is that it's been my experience that large departures from the main line of a big company's business are difficult to affect, right? So there's, over the years, they optimize for doing their job really well, and a bunch of network effects spread out of that, and some of it eventually implies that it's very difficult to change the direction of really any significant part of a large existing successful company. I'm convinced that that's a fundamental thing that's probably true all over. So if you want to build something relatively radical, I think it's more likely that you can find success in trying to build it from scratch in a new company than to try to kind of navigate the political and decision-making labyrinth in a big one to convince and align everybody that needs to be aligned in order to make a large departure.
Yeah, that makes sense. A paradigm shift, I think, as you both described it in our preparations before.
Yeah. Imagine the business plan. So we're going to build novel hardware with a brand new software stack in a world of a changing market. You go to a big company. I worked at Digital Equipment when they were going out of business, and the CTO told the research guys they should stop wasting time on research projects and just focus on things that are a $100 million business. Well, how do you know which one is a $100 million business? Right? You have to be able to say, we're going to go do this crazy thing, and then if it works, we'll be really happy.
Well, we wish you the best of luck. We'll look forward to hearing more on how that goes. That's all we have time for today, but thank you both so much for joining us. Thank you.